Okay. Okay, so I'll start with the question. Why should a bank be involved this early in quantum computing? And this is what a university professor asked me in Zurich earlier this year at the IBM Partner Forum. 5 years ago, I got this question more often, but I was surprised to get it again, right? So the implication is that we could wait and buy quantum solutions when they are ready, right? Especially maybe banks have this perception, right? I got the opposite opinion from Alan Kay. If you know Alan Kay, he showed the graphical user interface to Steve Jobs. Right? I had a one-on-one with him like 12 years ago. And he said, at your size, the company I was working for at that time, you should go as deep as create your own programming language. And that was his opinion. Now, the reality is that large banks, and I worked for 2 so far, they take a middle road. So we experiment early, but not at the scale. We don't create our own languages, but we always experiment early, and we build roads and bridges that are ready to be used later at large scale. And I can give some examples from my experience. We can also look at the history. So what happened with classical computing? Arguably, quantum computers are at the stage classical computers were in 1940s, right? Where they could solve toy problems, like printing the squares of the numbers from 1 to 100, right? And famously, the CEO of IBM at the time, Thomas Watson, he predicted the need for 5 computers in the whole world. 20 years later, almost every bank got a mainframe, right? So should we do something else now? Experimenting early? And the answer is yes. Another reason here, which I call smooth adoption, is if you look at this quote, it argues, I like this paper from MIT, it argues for being in the game early, but also it calls quantum computing a revolution. Right? Is it a revolution? Maybe. To the extent that it is, what do we do with computing revolutions in general? And our answer is, we treat them like evolutions. We don't like revolutions, right? We've been through mobile, so at some point or another, mobile, server-side, cloud, all of them have been called revolutions, right? And what we did, we were able to integrate them in a non-disruptive way, let's say. We do the same with quantum, right? So whoever claims this is a very different animal, we have to treat it in a special way, banks are not doing that, right? And I can talk again about my experience. Finally, we can learn from quantum solutions and apply them today in classical applications, like quantum-inspired. Again, I'll talk about that a bit later. So these stages, awareness, adoption, creation, I've seen them a few times. And Wells Fargo has entered the awareness stage a few years ago. Right? People did a good job, and I've seen this again at my previous place. It's just high-level talks. This is quantum exists, no technical or science concepts involved in the presentations. The next one is adoption, where you take what's already existing in the industry and you play, experiment, learn, right? So Wells Fargo was doing that. Vanyo Markov is here. He played with this before I went there. And by the way, it's always the case when you go to a new company, there is something there already, right? It's not like there is an external savior, right? So what we didn't do until this year was create new solutions and release papers. This year we have 6 papers, we'll have more, we're growing, but this is the stage we're in. Well, now one good question is, when do we adopt, when do we create? Right? So some banks may say, we never create, we just adopt what's there. We wait, and buy. And the question is, our answer is, we adopt in order to keep up with the industry. We create when we see that we can help with a need, and especially when it's a competitive advantage. You cannot buy a competitive advantage, right? Because if you buy something, anyone can buy, right? That's why we were offered, let's connect to data centers, with quantum encrypted. We know it's possible. We'll do it, right? Is it the time now? No, right? So that's the answer. When we create, we do it usually jointly. So let me talk about priorities here. Our priority is, and we've heard this from the previous speaker, they also have this quantum computing platform, which is the right way to approach quantum computing at the bank, right? You have to show something, solutions that work at a small scale, even now, right? Not just a bunch of papers that go out, we create headlines, right? So we like to visualize the platform as a pyramid. At the bottom, you have these quantum algorithms like Shor's, and fundamental things, quantum Fourier transform. We don't expect to create too much here. We adopt usually. We are focusing in these two layers, right? Where we create patterns and capabilities that apply to many problems, right? I went through design patterns in the 90s. We want to do the same. We create design patterns for quantum solutions. And then finally, we show solutions running at a small scale, right? These two layers. Production will come later. We're not promising, anything very soon. The focus is look at what problems will benefit from a quantum advantage. That's our main focus. For example, we heard from the business about limit order book, and we are attacking that problem, right? We are very pragmatic. Again, not a bunch of titles for papers. Finally, we want to learn internally and externally, right, as a community. How do we measure success? I think this was sort of a requirement for the presentation I included here. Internally, we measure success by the expertise we build, right? And the solutions we adopt. And when for the solutions, we look at two things. One is an advantage. So this quantum solution is better than a classical one. But we learn from the business that they actually use multiple solutions, multiple models, and they are happy to get another one to improve the average or the higher moments, So then we're not only looking at the advantage, we're looking also at an enhancement, right? Which is a lower standard in a way, right? Finally, we want to add to the body of knowledge whenever we can with papers, code, but papers and patents are not a goal in themselves, right? We're not going to count the patents because give me a number, I'll give you that number of patents, right? It's always, the papers are a reflection of the platform. If we don't have the code for it, we're not going to release that. Finally, a very important measure of success is managing the hype, right? I've gone through this with mobile, code generators. People would come and say, you don't have to do this, So it's harder on both sides to manage the hype. If someone is over-promising, right? So we're using these principles from Jeff Bezos. Bias for action, so you counter over-promises, inflated promises with that. Show it to me now. Don't tell me in 2 years, in 5 years, you'll have something. Deep diving, so we're fighting the inflated credentials. A lot of people are saying, they get a certificate, they are experts, they teach you. So we say, okay, show me. Show me the circuits. Right? And finally, frugality. Bezos says, this is a red flag. Someone wants to spend a lot of money, red flag, right? So we're trying to grow at a certain pace. R&D. So this is a small part of the advanced technology team, like I said. We have a mix of scientists and developers, right? About half-half. It's not only scientists who write some code for the paper. right? We want the solutions to go into the platform. So these are the areas we're looking at, again, pragmatically, based on the business needs. We're not going to do something because it's cool, right? So also, the platform supports both simulators and real computers, right? So it's made. Charlie, who is here in the audience, she's managing that. Finally, a very important pillar here is the in-house simulator that we have. And I have a slide for it. Why do we need our own simulator? Quickly going through, we have 6 papers this year, I think, like 4 or 5 in progress. First one, Samuel Chen is presenting this tomorrow at a different conference, reinforcement learning. I won't go into details. The other 2 are done in collaboration with IBM. So when I moved to Wells Fargo, the first collaboration I wanted to put in place is the one with IBM. I was used to it for 3 years before. So this one looks at a combination of reservoir computing and recurrent neural networks. Again, I won't go into too many details. This one is going to be presented at 3:30 in the technical track. So Vanyo, Markov, and Vlad will present this. These are all the papers at the beginning of the year. They are building blocks for financial engineering problems, right? You'll recognize state preparation. We have very efficient circuits for normal distribution, Laplace exponential. We apply the exponential and double exponential to differential privacy. Again, Vanyo will, here's a paper in the works. Inner products are everywhere. We did something with amplitude estimation. Yeah, this is the simulator. So let me talk about the simulator a little bit. Why do we need our own simulator? Right. The 4 use cases are listed here, but I'll start with another reason, teaching quantum computing. So we found out that in about 150 lines of code, you can cover the fundamentals of quantum computing up to phase estimation, Grover search, in pretty much any language. And we like multiple languages. We have Python, Julia, Go, Rust. So again, Charlie is maintaining this. She's teaching every month. She's teaching the rest of the company, whoever wants to learn quantum computing. On top of that, we have a sort of secret sauce for creating quantum states, preparing efficient quantum states. Vanyo created that. It uses genetic search. It discovers the structure and parameters for the circuit. And for that, if you use, for example, Qiskit, which is a great framework, it has a warm-up, like 5 seconds or so. But we execute this like millions of times, right, to find. So we found out we're better off with our own simulator, right, which is very fast. I have here graphs showing it's faster than QLAX, which is, in our experience, the fastest C++, the one that you can run on your computer, not HPC. Then we can generalize those circuits we find this way to more qubits. So we have the exponential distribution closed form. We'll publish soon. Another reason is for each circuit, we can, based on what gates we have there, what target, what controls, we customize that circuit. For example, SAM runs for 3 weeks. In one example, we have something running for 3 weeks on our side, IBM on their side, right? So if we speed up, if we customize the implementation per circuit, and you execute this circuit many times, then we get from 3 weeks to 1 week, right, or something like that for machine learning. Finally, classical shortcuts. In some cases, and I'll go to the appendix really quick, I had this on LinkedIn a while ago. The main advantages, 2 main advantages known in quantum computing are Fourier transform in Shor and reflections in Grover, right? These are complete classical implementations. So what we do is you give me a state, you got it with gates or whatever. I apply this classical implementation. I get the other side without gates. This is faster, right? So our simulator allows this kind of shortcut. What's interesting here is that both, if you look at this code, right? This is a reflection. You project, take the negative, and this is a reflection. It's a nice formula. Both of them contain inner products. This V dot, right? V dot, V dot. So the main advantage we see in quantum computation is parallel inner product. That's why you'll see a bunch of papers from us on inner product, right? As how much time do I have, Charlie? Okay, so let me just say this. The Nobel Prize was mentioned before, so I'll mention something similar. Reflections. We talked about reflections here. I realized, so my thesis was in groups generated by reflections, Coxeter groups. So I realized after a while that I used this formula pretty much every day in my grad school, right? While working on my thesis. The reflection formula. This is a book from my advisor. And what you see here is a kaleidoscope. We use the kaleidoscope, or I have one in my thesis, right? Reflections are a source of interference, right? If you play with a kaleidoscope, you have reflections. So, and you'll hear more about this, right? Because so once experts from different fields will come, well, they will realize, oh, I know a lot about reflections, and this is just a reflection here. Actually, it's two reflections, right, in Grover. Then I think you'll see more progress. We need more mathematicians, every multidisciplinary approach, and that's what we are looking to do. It's interesting if you know other sources of interference. I mean, waves is one, right? This is actually the sink, discrete sink, right? Created with waves, signal processing. Well, reflection is another one. And I don't know if you guys want to think about others. I know polynomials, right, in math. So we need more of those. And, and what I wanted to say, one result in my thesis was proved at the same time that someone who got the Fields Medal, which is the equivalent of the Nobel Prize. Margolis, he also got the Abel Prize. Some people say that is the equivalent, right? But this field is very important, right? If someone getting the Fields Medal looks at it, reflections are very important. And with this, any question?
Thank you, Constantin. Any questions from the audience? We have about time for maybe one question. Okay, taking one question from the audience here.
Thank you so much for the great talk, and I've been following your work for a while, and you've basically laid out a really nice framework for how we can start to get ready for actually taking classical data and keeping it in some sort of quantum register and being able to actually work with it with these algorithms. So I guess what are your thoughts on quantum RAM, and have you seen any like phase memory or other devices or other approaches that you may think are actually potentially helpful for your kind of applications?
So you are probably referring to the quantum dictionary, right? Which we put, it's in Qiskit. So in my former team, and by the way, we are proud to contribute to industry frameworks. We have Qiskit contributions, we have Penny Lane contributions. Sam is famous for LSTM. If you Google quantum LSTM, you'll find him, and the implementation is in Penny Lane, right? So the quantum dictionary is there. You can think of it as RAM, but it's not really, right? So you have the first register is the pointer, the key, and the second is the value. We call it dictionary. In fact, it's function encoding. And in the talk later today, Vanyo and Vlad will present hidden Markov chains with mixed states. So mixed states also require disentanglement of registers. So it's as close as we're getting to QRAM, but we're waiting for it. I don't know about any real QRAM. I don't know if it answers your question, but someone calls actually the dictionary, they call it QRAM, but it's not.